Welcome to Module 1 of this comprehensive course on perovskite solar cells. Before we can begin discussing complex device engineering, fabrication chemistry, or the analytical modeling of degradation mechanisms, we must first establish the absolute foundation of our field. We have to understand our fuel, light. The sun is a massive, continuous fusion reactor. It delivers more energy to the surface of the Earth in a single hour than all of human civilization consumes in an entire year. Our challenge in photovoltaics is not simply catching this light. It is a profound problem of thermodynamic energy conversion. We are attempting to capture a very specific flux of incoming photons and convert their kinetic energy into the chemical potential of electron-hole pairs inside a crystalline lattice. We then must extract those pairs as an electrical current before they recombine or degrade the material. Today we are going to dissect the physics of this incoming solar resource and establish the mathematics of how light interacts with solid matter. Whether you are fabricating devices in a glove box or writing computational models to simulate device lifetimes, everything starts with the optical generation profile we are going to define today. To properly model photovoltaic devices, we must treat light utilizing its wave-particle duality. Classically, light is an electromagnetic wave. It is characterized by its wavelength, denoted by lambda, and its frequency, nu. However, when light interacts with the lattice of a semiconductor, like a lead halide perovskite, it does not interact as a continuous wave. It interacts as discrete, quantized packets of energy called photons. The energy of a single photon is defined by the foundational Planck-Einstein relation, E equals h nu. That is, energy equals Planck's constant multiplied by frequency. It can also be written as energy equals hc divided by lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of the radiation. In semiconductor physics, measuring energy in joules is cumbersome, so we use electron volts, EV. 1 electron volt is the energy gained by an electron accelerating through a potential difference of 1 volt. Why is this equation the most important formula in photovoltaics? Because a semiconductor acts as an energy filter. It possesses a band gap, a minimum energy threshold required to excite an electron into a conductive state. If an incoming photon has less energy than this band gap, it cannot interact with the electrons. It passes right through the material as parasitic transmission loss. If it has more energy than the band gap, the excess energy is rapidly lost as heat, a process called thermalization. Therefore, knowing the exact energy of our incoming photons dictates what materials we must choose to absorb them. But the sun does not emit just one wavelength of light. It emits a broad, continuous spectrum. To understand this spectrum mathematically, we model the sun as a blackbody radiator. According to Planck's law of blackbody radiation, any object with a temperature above absolute zero emits a specific distribution of electromagnetic radiation. The surface temperature of the sun is approximately 5,800 K. If we plot the emission curve for a 5800 K blackbody, we see a massive peak. Using Wien's displacement law, we calculate that this peak occurs at around 500 nanometers, right in the middle of the visible green light spectrum. Evolution optimized the human eye to see perfectly at this peak emission. Similarly, as materials scientists, we must design the band gap of our solar cells to overlap optimally with this specific spectral distribution to maximize our energy harvest. However, the smooth blackbody curve is an idealization. The actual spectrum measured in space, just outside the Earth's atmosphere, is called air mass zero, or AM0. We use this spectrum to design solar cells for satellites. But terrestrial solar cells, the ones on our rooftops, must deal with the Earth's atmosphere. As light travels through the atmosphere, shorter wavelengths, like blue and UV light, scatter off gas molecules. This is called Rayleigh scattering, and it is why the sky appears blue. Meanwhile, larger aerosols cause me scattering. More importantly for our analytical models, atmospheric gases actually absorb specific bands of light. Ozone absorbs heavily in the ultraviolet region. Water vapor and carbon dioxide carve deep, jagged absorption dips into the infrared region of our spectrum. The light that finally reaches the ground is highly altered. To ensure solar cells are evaluated fairly across the globe, whether you are testing a cell at a research institute in Japan, Europe, or India, the photovoltaic community relies on a strict testing standard, the AM1.5G spectrum. Air mass defines the relative optical path length that light takes through the atmosphere. It is defined geometrically as AM equals 1 divided by cosine theta, where theta is the solar zenith angle, the angle of the sun from directly overhead. AM 1.5 corresponds to a zenith angle of approximately 48.2 degrees. This represents an average, clear, sunny day in mid-latitudes. The G stands for global, meaning the standard encompasses both the direct light from the solar disk and the diffuse, scattered light from the rest of the sky. Under standard test conditions, the AM 1.5G spectrum provides an integrated power density of exactly 1000 W per square meter. When you fabricate a perovskite device and place it under a solar simulator in the lab, That machine uses specialized xenon, or LED lamps, and optical filters to replicate this exact AM 1.5G curve. If your simulator calibration is off, your efficiency calculations will be completely invalid. Now, what happens when this 1000 W per square meter photon flux actually strikes our solar cell? Energy conservation dictates that the incident light has three possible fates. It can be reflected, transmitted, or absorbed. R plus T plus A equals 1. To achieve high power conversion efficiencies, we must maximize A. We minimize reflection using anti-reflective coatings, and we minimize transmission by ensuring the active layer absorbs the light before it reaches the back contact. But exactly how thick does our perovskite layer need to be? As light penetrates a material, its intensity decays exponentially. This is governed by the Beer-Lambert law, I of x equals I naught times e to the power of minus alpha x. Here, I0 is the incident intensity, x is the depth into the film, and alpha is the absorption coefficient. In computational materials science, $alpha is not just a random variable. If you are using density functional theory, often utilizing software like Quantum Espresso to model a material, you are calculating the fundamental electronic band structure. This band structure directly dictates the complex refractive index of the material, denoted as n tilde equals n plus ik. The imaginary part, k, is known as the extinction coefficient. It dictates how strongly the material dampens the electromagnetic wave. The macroscopic absorption coefficient is directly linked to this microscopic quantum property by the equation alpha equals 4 pi k divided by lambda. One of the primary reasons perovskite solar cells have revolutionized photovoltaics is that they possess extraordinarily high extinction coefficients across the visible spectrum compared to indirect bandgap materials like silicon. Because alpha is so massive, we only need a perovskite film thickness of about 300 to 500 nanometers to absorb the vast majority of above bandgap photons. Finally, why is the precise depth of absorption so critical for researchers? Because it dictates exactly where our charge carriers are born. This brings us to the optical generation rate, G of x. This function represents the number of electron-hole pairs generated per unit volume, per second, at a specific depth x. It is directly proportional to the absorption coefficient and the incident photon flux, G of x equals alpha times phi naught times e to the power of negative alpha x. When you are developing analytical models for perovskite solar cells, G of x is your starting boundary condition. It tells you where the charges originate. Furthermore, high-energy photons, particularly in the UV range, are absorbed very close to the front surface. This highly localized energy deposition is a primary driver of UV-induced degradation mechanisms at the device interfaces, a critical area of modern research. To summarize, our solar resource is a quantized photon flux, filtered by the Earth's atmosphere to the AM 1.5G standard and exponentially absorbed based on a material's complex optical constants. We have established how light enters the material. In our next lecture, we will transition into solid-state physics to understand exactly what happens to the electrons waiting inside, as we explore semiconductor band theory. Thank you for watching, and I will see you in Lecture 1.2.